Good. Okay, just a reminder that the first assignment is due at the end of this week. Please, if you need any help with it, just go in one of the lab consultation sessions. We've been trying to answer your questions on the forum. Yeah, there was a couple of, I think the figure for part 2 somehow, which accidentally regenerated the data file after generating the figure. So we've some of you pointed this out. So we've now updated the figure to match the data. Let me just find that. Yeah, index is back. Well, anyway, it's there. Yeah, this is the new figure. Okay, so today we're going to talk about recurrent networks. So we're going to talk about processing of temporal sequences, and we're going to talk about different approaches to this sliding window approach, recurrent networks, hidden unit dynamics, and long short-term memory. So there are many tasks. If you think what we've done so far, you've just given a single instance and then you have to give an output. So the stuff we were doing last week about the image processing is very impressive. You can give it an image and it'll tell you which category the image falls into, but it only processes one image at a time. It's not processing a whole sequence of images. But there are many tasks that rely on a sequence of inputs in time rather than just one input. So, for example, speech recognition or time series prediction, machine translation, handwritten recognition, and so on. There are quite a number of these tasks. So how can we design a neural network specifically for this one of these kinds of tasks? Now, some of the earliest work using neural networks, at least in this area, was the NetTalk system built by Terry Stanovsky and Rosenberg in 1987. And this was a system which would read in English text and then try to pronounce that text. So the inputs would be like this. One would read an input in the form of characters. You'd have a neural network, and then the output of the neural network would go into this speech synthesizer. We would choose between a bunch of phonemes, and then just for fun, they hooked it up to a speech synthesizer so they could actually listen to the output. Now, again, this is very, very early days of the rebirth of neural networks, only 1 year after the parallel distributed processing group met in San Diego. And the way they handled the temporal part of this is that the network took in 7 characters at a time. So in the middle is the character that it's actually trying to pronounce, and it's also given the 3 preceding characters and the 3 following characters. Now when you first look at this task, you might think, well, I don't understand why this why these extra inputs, why this context is needed, because, you know, if it's a T, it should be pronounced T, right? You'd think that. But actually, especially when it comes to vowels, you often do need some context. In English, at least, English has a lot of different kinds of vowels, and you often need context to figure out how a vowel should be pronounced. So if you think about how this A is pronounced in these different words, pa, pat, pate, paternal, there's actually 4 different sounds. Mo, mod, mode, modern. So it's flipping back and forth between a long O and a short O. So the task isn't as trivial as it might at first appear. Now, again, this very simple, old-fashioned neural network is a 2-layer neural network, and you have you have 7 groups of 29 inputs, because you've got these 7 characters, and 29, well, there's 26 letters in the alphabet, and you also have a space and a dash, and I think a full stop, you know, so you get a very minimal amount of punctuation in there as well. And it's a one-hot encoding. So if there's, you know, if it's a C, there's 29 inputs here. The one corresponding to the C is equal to 1, and everything else is equal to 0. You have a hidden layer with 80 units. And then you have 26 outputs corresponding to 26 letters in the phonetic, the International Phonetic Alphabet. So this is the character, the sound K. Now, this system gained a lot of media attention. They went on these, hooking it up to the speech synthesizer was very cute. And these guys went on a lot of sort of TV talk shows and demonstrated their system and got a lot of publicity. And yeah, in the early stages of training, the network's really just kind of starting to learn. It kind of makes this noise that sounds a bit like a babbling baby. And then when it's fully trained, it pronounced the words mostly correctly, but the speech synthesizer did sound somewhat robotic. So, from a point of view of publicity, this was a big success. A lot of people kind of criticized this. They said these guys are just media hounds. They just, they love to get themselves on the TV. But from a technical point of view, the neural network really didn't do that terrific of a job. And later studies have shown that actually just, a simpler machine learning system like a decision tree could have actually predicted the things with even better accuracy. And the other interesting thing, this approach can learn kind of short-term dependencies, but not medium or long-term dependencies. Well, that's obvious, I guess, because it can only learn dependencies which rely on inputs from the preceding 3 time steps, basically, or the next 3 time steps. So if for some reason the output for this character happened to depend on something that was more than 3 time steps in the past, the network would have no opportunity to take advantage of that information. It would just have to make a probabilistic guess based on the information that it currently has. So then we move on to simple recurrent networks. So this was an attempt to try to build a network which could retain information for a large number of time steps. Now the way this is called a simple recurrent network, or sometimes an Elman network, after Jeff Elman who introduced them. So at each, you know, part on the left looks like the standard kind of two-layer feed-forward networks we were looking at before, but in addition to the input, the hidden, and the output layers, you also have this context layer, and the dotted lines mean that the hidden layer, the activations of the hidden layer at the previous time step get copied to the context layer. So you feed in the first input, and you get an output, and then you copy the context, you copy the hidden layers to the context layer, and then at the second time step you feed in the second input. So when it says I1, I2, and I3, this is three inputs corresponding to one time step. Right? So the inputs for the second time step are fed in, and then there are weights from the context layer. So there's weights from the hidden layer to the input layer to the hidden layer, weights from the context layer to the hidden layer, and from the hidden layer to the output layer. So the weights from the context layer to the hidden layer, the idea is that because it's a copy of the hidden layer from the previous time step, this is an opportunity to retain information from before, and so you're given the next input combined with that information to produce the output. And theoretically, at least, this information could be retained for an indefinite period of time, but then the question is whether the network's actually able to learn to use information from far back in time. But at least it'll have a better chance than this windowing approach. It should be able to retain information at least for several time steps. Now, so this is sort of the full architect. This is what's really going on as we copy the hidden layer to the context layer, but sometimes we just, to simplify the picture, we draw it like this. So we have an arrow pointing from the hidden layer to itself, and we understand that this arrow is like one step back in time. So this is sort of happening synchronously, that you take the hidden activations from the previous time step, they get fed in here with a certain weight matrix, and then the inputs with a certain weight matrix, that all gets added up to get the next hidden layer, and then you have some output. Sorry, the letters have been, we use a slightly different notation here, but you get the idea. So then the question becomes, well, how do we train a network like this? And then, well, the answer is we use what's called backpropagation through time. So these recurrent if we know the length of the sequence, we can unroll this network into a feed-forward network, right? So this is called a recurrent network. Recurrent means running back into itself. So if we unroll this, we get a feed-forward network which will have the same behavior, but we have to know in advance how many inputs there are. So if we know that there are 4 inputs, then this architecture would behave exactly the same way as if it was like this, where each input is being fed in at one time step, and then the activations from the previous hidden layer are feeding in here. And it's weight sharing. So the restriction is all of these copies of the hidden units have to be using the same weights, and we're familiar with the concept of weight sharing from the convolutional networks we were looking at before. So once you say what's equivalent to this, then it gives you an idea how to train it. We train it by backpropagation, and we also backpropagate along here. So if we have a certain target output here, there are different tasks. Sometimes in some tasks, the network reads in a whole sequence and then only produces an output at the end. So one task in that category is language recognition. Like you read in a sequence and then you have to classify that whole sequence as either class 0 or class 1. So you would only make use of the final output. In other tasks, you may, sequence-to-sequence tasks, or for example, language prediction tasks, you may be producing an output at each time step, and you might have a target value that you're trying to match at each time step. So if you're only looking at the output at the end, you compare that to the target value. Based on that, you backpropagate the differential here and here, and then you backpropagate that differential here, and you kind of backpropagate like this. But because these weights all have to be the same, you accumulate the differentials, and then you make the weight updates. If you have target outputs at every step, you backpropagate from here to here, and then you also backpropagate this difference to give you a differential here. You add these two differentials. You backpropagate from here to here. You get a loss from here, and you add that differential to this differential, and so on. Fortunately, again, PyTorch will do this for us automatically because it's automatic differentiation. Now, depending on the task, sometimes, sometimes we backpropagate all the way to the beginning. Sometimes we only backpropagate one time step. So there are situations where we might only need to backpropagate one time step, and the network might still learn. If we want to backpropagate all the time steps, then of course we have to keep all of these intermediate values in memory, because once we get the output here, we have to have retained all of these intermediate values so that we can do the full backpropagation. If we backpropagate only one time step, then we don't have to keep everything in memory. We only have to retain the one previous value. Any questions about this? Now, that's the sort of basic architecture. There are some variations on this theme. So sometimes it's useful to add in these shortcut connections that we saw in another context. So we could have shortcut connections that go directly from the inputs to the outputs. It's also, I haven't drawn it in this case, but sometimes the outputs are also, sometimes the outputs from the previous time step are fed into the hidden layers. That's sometimes called a Jordan network, although that's less common these days. Now this is, I just mentioned this is some work I did some years ago in this area. This is just gives you an idea of the variety that we can have with these architectures. So this is called a second order network, or sometimes called a gated network. The way this works is as follows. You're reading in a sequence of zeros and, so the task here is you're reading in a sequence of zeros and ones, and you have to classify that sequence into one of two classes, and you have this hidden unit activation here, and then depending on whether this is a 0 or a 1, you choose one set of weights or the other set of weights, and using that set of weights, you get the next value of the hidden units, and then this gets copied back. So this is sort of the reason someone's called a second order network is because it's like you're multiplying these weights by, depending on this input, you might be multiplying these weights by 0 and those by 1, or vice versa. I mean, the details of this, so it can be written out as if it's like a product, or it can be thought of as a gate switching between two different networks. So we can start to look at the hidden unit dynamics the same way we looked at the encoder networks. So let's think about this formal language recognition task. So again, we're a long way from natural language here. We're just looking at various sort of formal languages. But the idea here is to learn a rule that you're given two sets of sequences, and they're in two different classes. So we've got the accept class and the reject class. So what rule would you, if you had to come up with a simple rule to say which sequences to accept and which to reject, what would be the rule? That's right. Yeah. You only accept sequences that consist of all ones. If there are any zeros, you reject. Right? Now, a language or a rule like that can actually often be described in terms of what's called a finite state automaton. So I'll just explain how this works. So these are states here. These circles are states, and these arrows are transitions between states. And this arrow shows that this is the start state, and then as you read in the sequence, you follow the arrows. So as long as you're reading ones, you stay in this state, but as soon as you read a zero, you go over to this other state. And then once you're in this state, no matter whether you read a 0 or a 1, you stay in that state. And the double arrow here means that this is an accept state. So if you end up in this state with a double circle, then you say that you classify the string as an accept string, and if you end up in another state, then you classify it as reject. So this finite state machine exactly accepts the language that you described. It'll accept only those strings that consist entirely of ones. And the interesting thing is, we can train, if we train the recurrent network, it actually mimics the behavior of this finite state machine. So this, this is a plot from of activations that we get when we feed in certain, after the network's been trained. What happens is the network starts in this state, and if every time if we keep feeding in ones, these little dots here are the states it goes into. These are the two hidden units, and these are the states that it goes into while we keep feeding it ones. And then as soon as we feed it a 0, it goes over here, and then no matter whether it's a 0 or a 1, it stays in this region here with these dots. And this line here is the dividing line between accept and reject. So it accepts things on this side of the line and rejects things on that side. So you can actually see the sort of dynamics of this language recognition task. Now this one is slightly more involved. Can anyone tell me a rule that, can anyone come up with a rule that distinguishes these two classes, accept and reject? 3 zeros, very good. So if the sequence contains 3 consecutive zeros, we reject it, and otherwise we accept it. And again, this is sort of, this is a finite state machine that implements that language or recognizes that language. So this is the start state. Whenever you see a 1, you go back to the start. Whenever you read a 1, you go back to the, if you see the first 0, you come to here. The second 0, you come to here. The third 0, you go to there. If after 1 or 2 zeros you read a 1, then you go back to the start and start counting zeros again. So these states are all accept, but if you do see 3 zeros in a row, you end up here, and then you stay there. Right? And this is this shows the network that's been trained on this task, and you can actually, there's an algorithm you can use that will actually extract out this machine from these dynamics, and yeah, basically it starts here, as you reach here, so it progresses to here, and then eventually up to there. So it often happens that the network exactly mimics the behavior of a finite state machine, but while it's being trained, sometimes it exhibits dynamics that can't be fully captured by a finite state machine, and sometimes we can see a sort of phase transition from one to the other. So this is after a certain number of epochs of training, when we process random strings, we get this kind of these dots are all the activations that can occur, but then at the next training step it becomes like this. So it's become like here it's learned what we call a language that can be recognized by a finite state machine is called a regular language, whereas this is recognizing some kind of irregular language. So this is, again, I don't know how familiar you are with this. This is not crucial to the course, but if you've studied formal language theory, there's this thing called the Chomsky hierarchy of classes of language, formal language, and the kind of machine that can recognize them. So something that can be recognized by a finite state automaton is called a regular language. If it can be recognized by a push-down automaton, it's called context-free. And then there's something called a linear boundary automaton, context-sensitive languages, and then you get like recursively enumerable languages. And an example of a language which is context-free but not regular is A to the N, B to the N. So this so what does that mean? Well, every time you have a sequence of A's and B's, and however many A's, you're allowed to have any number of A's, but then it has to be followed by an equal number of B's. So if you have one A, you've got to have one B. If you've got two A's, it'll be followed by two B's, and so on. And in this case, we're treating this as a language prediction task rather than recognition. So the first B, we're not able to predict when the first B will occur, but if we see a certain number of A's and then we see the first B, we know that there's, like, let's say we've seen 3 A's and then we see a B, we should know that there's going to be 2 more B's and then an A. Right, so those are the things we can predict. So this was some work that Ellman did later with Janet Wiles. What happens if we try to train a network on this task? What kind of behavior will emerge? And here they used a simple recurrent network to try to predict the task. So we've got a one-hot encoding for the input and a one-hot encoding for the output, and we try to train it on this task. And the interesting thing is that this is the kind of dynamics that emerges. So what's happening here is as you process the A's, it's being given 8 A's followed by 8 B's. So as it receives the A's, you get this kind of decreasing oscillation towards the point here. And then when you process the first B, it jumps over to here, and then with the next B's, it kind of oscillates outward from this point and eventually crosses the line to predict. So this is, anything on this side of the line, it's predicting a B, and then on this side of the line, it's predicting an A. So this is sort of interesting because it's able to generalize to a larger number of A's or B's than what it was trained on. So this, there's no, there's no finite state machine that will predict this, because you need a different, effectively you would need a different state for every value of n. You would need to have a different state. So I think what they expected to happen was that it would maybe learn a finite state machine that processes n up to n equals 10 or so. But the interesting thing about the solution it actually comes up with is you only train the network up to n equals, you only train it up on examples up to a to the n, b to the, a10, b10. So it only ever sees 10 consecutive A's while it's training, but when you test it on 12 A's, it makes a correct prediction, because it just oscillates a little bit closer to this point, and then it takes a little bit longer to oscillate away from this point. So it's interesting because it exhibits generalization beyond like a finite state machine. Now, some later work, we later found that if we trained these networks by a process called evolutionary algorithms, we could actually get a more stable solution. But sometimes the evolved solutions had a monotonic rather than an oscillating behavior. So the oscillating behavior went like this. Sometimes you get a solution where it stays on the same side. It stays on the same side, but again, it goes exponentially closer to here, and then afterwards exponentially away from this. And you can do a kind of, you can analyze the dynamics of this by looking for fixed points, doing a linear approximation around the fixed point, and then diagonalizing the matrix and so on. There's ways of kind of analyzing these things. And we also looked at the problem of balanced parentheses. Right? So the balanced parentheses, the task here is you have to have the same number of A's and you have to have equal numbers of A's and B's, but they can occur in any order as long as you've always seen more A's than B's. So it's easier to think of this as opening brackets and closing brackets. You go open, open, close, open, close, close, for example. So I think if in first year programming, we often set this as an assignment that you have to read in a string of open and close parentheses and say whether or not it's balanced. So this is training a network on that task. And here, the interesting thing here, it counts up the number of, it keeps track of the excess number of, it keeps track of how many more A's have I seen compared to B's by spiraling. So as you process, you start here. As you process the A's, you go, you kind of spiral inwards like this, and then when you see some B's, you start spiraling outwards, and then when you see A's, you spiral inwards again, and then outwards again, and at the end, it can tell whether the number of A's and B's matches. Yeah, so again, it's just an interesting kind of way of analyzing the dynamics. And you can also, apply the same kind of analysis. You can find the fixed point and then linearize, but here the eigenvalues are actually complex numbers because it's a spiraling action. So then we thought, well, that A and B n is interesting, but what about A and B and C n? This is, for example, a mildly context-sensitive language, and it is actually able to learn. So you have 3 inputs now, 3 hidden nodes, 3 outputs, and I think we had some shortcut connections as well. It is able to learn this, and the dynamics are quite interesting. So as it learns the A's, it's spiraling inwards, and then as it learns the B's, it's spiraling, well, in one direction, it's kind of counting up and down simultaneously. In one direction, it's oscillating inwards in one direction and outwards in the other direction. So it's counting. It's oscillating outwards to check that the B's are equal to the A's, and then it's oscillating inwards in a different direction so that it'll later be able to check whether the C's are equal to the B's. And sometimes you get monotonic solutions as well. Okay, so that's sort of about as far as you can push this thing with these simple recurrent networks. They can learn these kind of simple languages. They can learn to count up and down. They can remember a limited amount of information, but they can't learn like really complex things, and they have difficulty learning long-range dependencies because you notice that this is kind of unstable. In order to learn A12, B12, like these oscillations are getting smaller, and if there's some noise in the network, it could kind of lose track of where it's up to. So what we really want is an architecture that would be able to learn long-range dependencies. So in sort of real language tasks, the output here may depend on something that happened many time steps before. For example, pronouns. So what are some examples of this? Well, pronouns and reference. So, my son went to the dentist, and the dentist told him that he has to brush his teeth more often, or you switch the gender. You know, my daughter went to the dentist told her that she has to brush her teeth more often. So some languages have this kind of distinction of masculine and feminine pronouns, and sometimes you have to remember, from the beginning of the sentence or even the previous sentence, whether the pronoun should be masculine or feminine, whether it should be singular or plural. It might make a big difference. The pronoun, you might be able to tell what the pronoun is referring to only because of its matching the gender or the number. And there are various other examples like this. Like often the meaning of this word really depends on what happened before. So in the late 1990s, Hochreiter and Schmidhuber were struggling with this, and they came up with an alternative architecture which is called long short-term memory, which is able to learn these longer range dependencies. And more recently there was a sort of something similar but a little bit simpler called the gated recurrent unit. And these are two excellent sources for describing this long short-term memory. And I highly recommend these, and I've taken some of my slides from this Christian Herter blog in particular. So here's an example of a toy problem where we need to remember long-range dependencies. So again, so these are it's good that we discuss these finite state machines because now we're looking at them in a slightly bigger scale. So this is a Reber grammar and this is an embedded Reber grammar. Now what this means is you've got, this is the start state, and then the net, so an example of a string that might occur in this language is as follows. You just have to pick which arrows to follow. So the following string might occur: B, T, S, S, X, X, T, V, P, S, E. That's an example. Or you could have B, P, T, 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 V, V, E. Right? So any string that'll, if you just follow through these states and pick one of the letters with the arrow pointing in the correct direction, can generate different strings. And the task here is a prediction task. So the network at each stage is trying to predict the next letter, and if 2 letters are possible, then it should predict each of them with equal probability. So it should predict B first, but then it can predict. So there's 7 letters altogether: B, T, S, X, P, and E. B, T, S, X, P, E, and V. And so there's 7 outputs. I haven't drawn the explicit architecture, but it's basically the same. You can try to train a simple recurrent network on this. You need 7 outputs because there are 7 letters, and normally we have like a softmax at the output layer, and the input layer, you also have 7 inputs, which tells you the most recent letter, and you can train this. And actually a simple recurrent network, I think, would be able to, if you worked actually, that Christian Herta tutorial goes through this, but it's not in PyTorch, it's in Theano, which is a bit out of use these days. But you can actually train a simple recurrent network to learn this grammar. So if it gets, when it's after reading the B, if it's in one of these states, it'll predict T and P with equal probability, or here it'll be T and V. So sometimes it predicts things with equal probability, but when it gets to here, it'll predict the E correctly. Okay, so it can learn this, but then we go to this embedded Reber grammar. Now this is where things get sort of nasty. So the thing in the box is just the same as the Reber grammar I showed you in the previous slide. This box is the same as that box. But we have this extra twist that after the first character is always B, but then with equal probability we have T or P, and then we can spend an unlimited amount of time inside here, but at the end we have to remember what we saw at the beginning, right? So there may be 20 characters occurring here, but then when I get to here, I have to remember the fact that I saw a P at the beginning and not a T, and vice versa. So it's sort of a bit of an artificial task, but it's it requires this kind of these long-term dependencies. So if you try to train a simple recurrent network on this task, it will fail. It'll do this part correctly. It'll predict all of these things correctly, but when it gets to here, it can't remember where it came from, so it'll just predict P and T with equal probability. Okay, but an LSTM can actually learn this. It can remember. It's got the capacity to remember, learn to remember what it saw before, even though it could be an unlimited time period earlier. Okay, so let's just go through this long short-term memory. So I might actually try to bring up this blog if I can. See if I can click on this. Let's see. Okay, so that's a recurrent network. That's a simple recurrent network. This is the backpropagation through time. Okay, so this, what's drawn here is a simple recurrent network, but just drawn in a slightly more elaborate way. So you've got the input coming in, you've got the hidden unit from the previous time step. These are combined with, there are weights here and weights here, and then it goes through the tan H function, and that gives you the next hidden unit. So this is just like as a point of comparison. So this is a simple recurrent network. Now, the long short-term memory adds some extra complexity. So you have what's these little gating units. So you have a forget gate, you have a forget gate, forget gate, an incorporation gate, and a remembering gate. Yeah, and somehow they seem to need these three gates. Yeah, the gated recurrent network later cut it down to 2 gates, but some people still think that these 3 gates are needed. Okay, so let's go through these. See if I can zoom in here. Oh, that's the best I can do. Okay, so it zoomed the text but not the figure. All right, so this is the forget gate. So this is a sigmoid. So the actual hidden units vary between -1 and 1. We've got this tan H to so the actual hidden units, there's a certain number of hidden units, and each one varies between -1 and 1. And so we've got these activations here, and then this sigmoid gives you a number between 0 and 1, and that the context layer at the previous time step gets multiplied by that. This is really, I can't, I can't rescale this back now. Let's see if I can just open it again. Control 0. Oh, thank you so much. Okay. Right, so there's a multiplication here. So the previous context is coming in. So, well, first of all, we've separated out the context and the hidden unit. They're kind of like 2 separate things. So the previous context is coming in here, and this sigmoid is giving you. So you think of this, every hidden node. Let's say there's 10 hidden nodes. If there's 10 hidden nodes, there'll also be 10 context nodes. And what you're getting here is a number between 0 and 1 for each hidden node. So you're getting 10 numbers between 0 and 1. And then this gets multiplied by that number. So if sigma is 1, let's say for context unit 1, sigma is equal to 1, let's say. Well, that means this gets multiplied by 1, so it gets remembered completely. if for context unit 2, sigma is 0, this gets multiplied by 0, so that means that unit gets forgotten, the value of that unit gets forgotten because it's multiplied by 0. If this sigma is a half, let's say for the third context unit, maybe the sigma is a half, so that means it gets multiplied by half, so it's kind of like partially forgotten. Right. So this tells you how much of each component of the context to forget and how much to remember. That's the first stage. Then you take the previous hidden node and you have another gate here, which is the, I think I stands for like inclusion, I think was the word that I was struggling for before, incorporation or inclusion. So what's going on, you see this tan H here, so this is computing a new value for the context. So this is doing the same job here this little piece here is doing the same job that the recurrent neural network would have done. So it's computing a new context value, but then this gate is telling you how much of that new value to incorporate into the old value, because that's going to get added. So you've got the old context coming in, you've forgotten part of it, and then you add in a new part. Right? So this kind of gets, so again, the same kind of logic. If this is equal to 1, that means you want to incorporate all of the new component. If this is equal to 0, that means I want you to forget, don't include, if the fifth unit has 0, I want you to multiply that by 0. So don't include any of that component, right? So this is kind of done component-wise, and then those things get added together. So this, what's here is a linear combination of the previous context unit partially forgotten, plus the newly computed context masked by this incorporation thing. So that, so that's this part here. So this is the forgetting part, and this is the inclusion part. And then you have yet another gate. So that comes along, but then this, those get added, and then you apply tan H to bring it back between -1 and 1. And then a third gate is the forgetting gate. So whatever's been, so that gives you the new context unit, but then this here gives you the new hidden unit. The two things are different. And again, this gate here tells you what to remember. So if this sigma is 0, it tells you not to remember that component, and if it's 1, it tells you to remember all of that component, and if it's in between, you partially remember it. So this is the full architecture. So it seems a little bit complicated, but there is a kind of logic to this. Yeah, so you're forgetting parts and incorporating new parts and then remembering parts. And all of this is trained by backpropagation. And somehow this works. Now, I mean, the best way to think of it, we talked last week about later work with residual networks, with image processing and these skip connections in these deep image processing networks that copied activations from one, bypassing certain hidden layers, and then whatever came out of those hidden layers got added on. This is actually earlier work, but it's the same principle that because of the back propagation can sort of bypass back propagation can sort of bypass this, and you try to remember whatever the idea is that these gating networks should try to figure out which parts of the context carry important information and which ones don't, right? So you can learn to remember those units which are carrying vital information and replace the others. And I mean, this is a bit hand-wavy, but I suppose if you think about it in just this embedded Reba grammar, it could potentially learn to have a specific unit whose job is to simply remember whether you saw a P or a T, and then that unit could be preserved while you're processing this. That unit, the value of that unit could still be preserved and then read out at the end, right? So it's just a matter of it would have to learn that this remembering gate should be 1 for that unit, and maybe but the inclusion maybe will be 0. So that guarantees that this information would be preserved, whereas irrelevant information will be discarded. Okay. Are there any questions about this? I mean, when I first read Hochreiter's paper, I really struggled to understand what was going on. But I think this blog makes it a lot clearer. Now, somewhat later on in 2015, someone came up with this. People kind of struggled with this. People thought, well, it's a nice idea, but people couldn't really. This is exactly the same thing, but it just shows you it just makes the weight matrices explicit. There actually are weight matrices connecting these things before it goes through the sigmoid or the tan H. Now, some people looked at this and said, well, I like the idea, but I can't really understand why you need three gates. It always seemed a bit excessive to have 3 different gates. Surely there's a way to do it with 2 gates. And so eventually people tried various different things and came up with this architecture here, which is called the gated recurrent unit, or GRU. And the way this works, you basically, instead of having separate forgetting and remembering gates, you have one gate which determines both, and it's saying, well, I'm going to take a mixture of something times this and one this outputs sigma, then I'm going to multiply this by sigma, and I'm going to multiply that by 1 minus sigma. Saying, okay, the next hidden unit should be a weighted average. In each component, the next hidden value should be a weighted average of the previous hidden value plus the new hidden value. And so instead of allowing those things to vary independently, I'll just say it's going to be sigma times one thing plus 1 minus sigma times one thing plus sigma times the other thing, and I'm just going to learn sigma, right? And so basically that's what's going on here. So 1 minus sigma tells you, determines how much to forget, and sigma tells you how much of the new thing to include, and then there's this gate here. So it's very similar to the LSTM, but with only 2 gates. And it was sort of, this came out in 2015, and a lot of people, there was sort of a lot of excitement about it, and a lot of people, there were a lot of papers claiming that this architecture was better than LSTM's, or equally good and simpler. And I think a lot of people kind of didn't like Schmidhuber, and so they didn't want to cite his paper, so they preferred to use this architecture. But more recently, there's been another series of papers that actually say that LSTMs are better than this. And so it's sort of hard to know the current thinking, but probably the LSTMs are more reliable than this, but no one exactly knows for what reason. But somehow these 3 gates do seem to give you a bit more reliable performance. Yeah, but anyway, the 2 things are similar and often do a similar job. So, yeah, just to kind of summarize, so we've looked at 3 different ways of handling temporal sequences. Yeah, the sliding window approach can only learn from very short range dependencies. Simple recurrent networks can learn medium range dependencies, and the long short-term memory can learn long range dependencies. Any questions about this? Good. Okay, we'll take a 10-minute break, and then we'll talk about language processing. Yeah.
Because if we're trying something like that, we add another list structure to there, so we can finally confused whether it is P from the beginning or T from the beginning.
I mean, it's happening component-wise, so it's when it's added, like if this sigma is 1 and that, like let's suppose for a particular component this sigma is 1 and that sigma is 0, well in that case it would just be, when you add them, it would just be taking that component from here. And conversely, if this was 0 and that was 1, it would be taking that component from here. So it can, adding can have the effect of just selecting. It can act like a modulator. Okay, I'm going to take some components from this and some components from this. But if the sigmas are between 0 and 1, then yes, it can actually be sort of mixing them up or averaging it.
Is this using
Well, I see what you're saying. Yeah, it's not drawn here, but actually you would put an output layer. This is the hidden units, and then you probably put an output layer on top. You probably put a linear layer on top with a softmax to do the prediction. Yeah, they haven't kind of drawn the same way here they draw the hidden units, they don't actually draw the outputs. You would have a separate output layer on top of this with 7 outputs. You have a linear layer on top of this with 7 outputs with doing a softmax prediction.
Thank you.
These correspond to like the different pronunciations, or what do these four correspond
This is
to?
just the input. So, well, there's 4 drawn, but it's actually 29. There's actually 29. So there's one input for A, B, C, D, E, F, G. So only the C input is equal to 1, and everything else is equal to 0.
Yeah, I didn't get that. So when you say 7 groups, you're considering only E sound and C sound, only these sounds, is it?
The input is what's written. The output is the sound. So there'll be different. This sound here is K, but there'll be different outputs for O and O. So the output is actually here.
Okay, this is the output.
No, sorry, the sound is actually here at the output. The input is not the sound, the input is just the writing.
Yeah, so, and each group would it have 7?
Well, you're looking at 7. You're looking at 7 characters. So you're looking at the middle character, and then the 3 before, and the 3 after. So that's why there's 7.
Yeah, this
There's
sliding
7.
window
The
size.
sliding window size is 7, but for each of these you have 29 inputs.
Okay, 29 into 6, 3 empty characters.
3 pronunciation. Yeah, the space attached. Dog,
This one which we were just talking about, which we were talking about in the
Yeah.
Here, are we trying to predict which is the next character?
That's
or are
right.
we trying to predict, given a string, is this a valid string or not?
Here we're just trying to predict the next. There's 2 different tasks. There's some recognition is where we're trying to say if it's a valid string or not. But here you're always given a valid string, but you try to predict the next character.
Given if I convert this into, make this E into B,
Yeah.
wouldn't it be equivalent to this? Because in a way I'm having to remember B and B here, right? So if I change this E to B,
Yeah, but when you get to this state, you know that it's B. Well, here you don't know whether after you've been in here for a while, it may be hard to remember whether you're in here or here. Like if you've seen T, S, S, X, X, V, P, S, E, you might get confused, am I here or am I here?
okay, here there is just one string.
That's right.
Question regarding the backpocket abbreviation
Yeah.
times. You would say previous times for the entire given layer or for one given
The whole layer.
entire layer. Okay. So when you say you can remember indefinitely,
Well, it depends what kind of information. So, I mean, with these examples, oh, okay. It didn't show, but there's another example where you would set strings that have an odd number of zeros, and so in that case, if there's a 0, you go back and forth between the 2 states. So in that case, you can actually remember indefinitely, but it's a very simple information. You're just remembering whether it's even or odd. So you're kind of remembering one bit of information indefinitely. But the LSTMs can learn more sophisticated information. But the other thing is the length of the strings. Like, yeah, if you often you can learn just by backpropagating one time step as long as there's as long as you're trained on strings of every kind of length. You know, if you're only trained on strings of length 10 and not shorter ones, then you may have trouble learning this kind of thing.
Okay. Thank you.
Hey, good day. Actually, this is a question.
Oh yeah.
But I think you mentioned something cool in the science back but you mentioned average score. Or did I just read it somewhere? And I'm trying to work out, when would you use the average score?
I don't think I mentioned it, but I have seen it. The only place where I've seen average pooling is where you have a fully convolutional network. So, I mean, there are some. So let's suppose you want to.
I was trying to think what would you be looking to find?
Well,
like fur rather than a feather.
Well, let's say there's a task. So one of my students have been looking at is like object segmentation. So let's say you know there's a bird in the image. You want to know not just that there's a bird in the image, but you want to know where the bird is roughly in the image. So you can have what's called a fully convolutional network. So you go through several convolutional layers, and you don't have any fully connected layers at the top. But you do end up with something. So whatever the original image might be, you know, 128 by 128, but you end up with something that's 7 by 7. And then you do an average pool you do an average pool. So, but then if you want to know whether there's a bird in that image, okay, you train it on recognition, right? So let's say you're not told where the bird is, you're just told that there is a bird. So you've got this 7 by 7 network. So you've got 49 activations here. Oh, sorry, you've got a 7 by 7 network. You average the activations in all of these 7 by 7 things, and then you put a linear layer on top. So you may still have multiple channels. It's 7 by 7, but let's say there's still 16 channels. So for each of the 16 channels, you average over this 49 values. That's average pooling. And then you put a linear softmax layer on top to learn the object. And then, well, some of this is good for classification, but then the advantage then is you can actually kind of get an idea where the bird is by looking at the weights. Like when you look at the average pooling, you say, okay, well, which part of the image is most responsible for that classification? So it's just usually at the last layer.
Thank you.
I have one quick question.
Yeah.
It was also about convolutional layers. I was just wondering if you have, for instance, this image, which has one channel. Why is it N1 channels in the convolutional layer? Is it because you have N1 different
Features.
Or kernels? Is it
Different kernels, that's right, exactly.
okay, so you have that many different kernels,
That's right,
and each kernel looks for one kind of feature?
exactly.
Okay. Then I understand. Yeah, okay, nice, perfect. Thank you.
Okay, so far we were looking at kind of toy examples in a way, these simple recurrent, these kind of finite state machines, finite state automata and formal languages. Now we look at how we can scale these things up and try to apply them to real language processing. Yeah, so we look at statistical language processing, n-gram models, co-occurrence matrix, word representations, word-to-vec, and your machine translation. I'm not sure if we'll get to all of this today, but we'll make a start on it. So, synonyms and taxonomy. So, what is the what is the meaning of meaning? That sounds very philosophical. So, if you want to know the meaning of a word, you could look up a dictionary, and you will see a definition there. And you can look at synonyms and antonyms. You can look at synonyms and antonyms. So synonyms is words that have a similar meaning, and antonyms is meant to be words that have an opposite meaning. And then you can look at taxonomy. So penguin, a taxonomy or an ontology is like a penguin is a bird, and a bird is a mammal, and a mammal is a vertebrate, and so on. So you get these kind of hierarchies of one thing being another. So these are sort of traditional ways of looking at language. So if you look at a thesaurus, there's a lot of online thesaurus. You look at thesaurus online now, type in a word and look at lists of synonyms and possibly antonyms. And these taxonomies are built up into resources like word tree. I think I briefly mentioned last week about this YOLO system. It tries to classify objects as, a dog and then as a specific type of dog and so on. Now, so these are kind of traditional approaches. Now, what's the drawback with this? The synonyms aren't too bad. So this is synonyms for the word elegant: stylish, graceful, tasteful, aesthetic, and so on. That's pretty reasonable. I mean, if you had a sentence with the word elegant in and you chopped out elegant and replaced it with one of these other words, you'd probably preserve the meaning pretty reasonably. Antonyms are a bit antonyms are a bit more kind of odd. So, what's the antonym of black? You might say the antonym of black is white. But really, black and white in some ways, is black really the opposite of white? Well, it is in a way, but the words black and white actually are very similar because they're both colours. Right? They're opposite colours, but they're both colours. So if you have a sentence with the word black and replace it with white, you get a meaningful sentence. I saw a black swan last week, I saw a white swan last week. That made sense. Whereas if you replace it with some other word, it won't make any sense. So black and white, they often occur in the same kind of context. So it's really kind of a fiction to think that one word can really mean the opposite of another. It would be more accurate to say that words share certain features. So two words may have certain features in common and others different. So the words king and queen are very similar. They both refer to a ruler, but one is male and one is female is the difference, right? So what we would prefer is a system which actually gives us more detailed information about the different similarities and differences, in pairs of words. Another issue is that these things require human effort to compile. So historically, someone went through and looked for synonyms for elegant. It's not an easy process to if you just sort of sit down in your armchair and try to think, oh, what's the word that means elegant? You might not think of all of them. So I think classic, like Roget's Thesaurus, I think they got a team of people to read through tons and tons of text and look out for words. Okay, does this mean something? What are the categories I already have? And so on. So you've got to be more systematic. And I guess Samuel Johnson, who compiled an early English, he didn't compile the first dictionary, but he had the first dictionary where he tried to include every word, and also for each word he had a sample of a nice phrase for that word. And again, he didn't do it by just looking at the word and trying to think of a phrase. He hired a team of 7 Scotsmen to read through great works of literature, and every single sentence that they read, they would be thinking, oh, maybe that's a good example. They'd come across something, oh, that's a really good use of that particular word, and they'd copy that down and file it somewhere and so on. So it's kind of like done the other way. So a huge amount of human effort required to compile these things. And so it would be nice if we'd be able to get this kind of information automatically without human effort. Yeah, because it's, as well as using up people's time, they may be incomplete. There are always things that humans might miss. Okay, so how can we just take some text and try to analyze it statistically? Well, I've chosen this nursery rhyme just as an example to move on with. Excuse me, one of my favourite nursery rhymes, yeah. There was a crooked man who walked a crooked mile and found a crooked sixpence upon a crooked stile. He bought a crooked cat and caught a crooked mouse, and they all lived together in a little crooked house. So how can, if we're given a text like this, how can we analyse it? Well, one thing we can easily do is just count the frequency with which certain words occur. So here's a list of all the words in that text and how many times they occur. Now, there are some words that occur frequently in most documents. So words like and the, pronouns tend to occur commonly. So the word a occurs 7 times in this text, for example. Some words occur frequently in a particular document, but not generally. So the word crooked appears 7 times. Now you may think this is unnatural, but in fact this exemplifies something that's very common. For any document that I show you, it's often the case that there's a few words that occur a lot in that document and not much in other documents, depending what it is. If the document is a newspaper article about banks, then the word bank will occur, right? Many times, potentially. If it's a manual describing how to use a lawnmower, then the word mower will appear. So every documents tend to have a particular subject matter, and so that's often, you get words that occur many times in that document. And that can be useful for document classification. Certain words may occur a lot in certain types of documents and not others. So there's this task of document classification where you're given a document and you have to just classify it into multiple. Is it a legal document? Is it an instruction manual? Is it an opinion piece? Is it a newspaper report? Or sentiment analysis? You're given a review of a movie. Is it a positive review or is it a negative review? Based on that review, should you see the movie or not see it? If a stock is if a stock on the stock market is mentioned in an article, should you buy the stock or not? Different things like this. Okay, so let's think about document classification. We could, if you want to train a system to do document classification, you could have a large number of training documents. Let's say you've got 10,000 training documents. You could make a list of all the words in the English language or all the words that occur in any of those documents. And then you could count, for each document, you could count how many times that word occurs. And based on this information, you could perhaps, if I tell you the classification of those 10,000 training documents, then when you see a new document based on all this, you may have a good chance of trying to say what kind of document the next one is, right? So in this approach, every column of the matrix represents this is a matrix, right? So the rows of this matrix are indexed by the words in the language, and the columns are indexed by the documents. So if you had 10,000 documents, the number of words in the English language is about 50 or 60,000. So you could get it's a pretty big matrix. You get a matrix that's with 60,000 rows and potentially maybe 10,000 columns. Now what you find is certain words tend to occur in children's books or rhymes. You know, cat, mouse, house. If you're familiar with the work of Dr. Seuss, or if you've looked at some children's books, they're much more likely to contain the word mouse or cat than a legal document, for example. Right? But there'll be other words that often occur in legal documents, or political news, or sporting, or whatever. So you should be able to tell what type of document it is from this matrix. Yeah, so basically, if the values for certain words are high, then you would be likely to classify this document in a particular way. Now, words, I mentioned this thing that a document may, there may be certain words that occur a lot in that document. So, if this is we're talking about here is essentially a linear model. So, the fact that the word occurs once is significant. The fact that it occurs 7 times, if you weight that factor by a factor of 7, you may be giving undue emphasis to that word. So often what happens is, instead of actually putting the number of occurrences in here, we simply put a 0 or a 1, showing whether the word occurs or not. If the word occurs, you put 1, otherwise you put 0. These are the two simplest methods. Of course, you can do intermediate approaches. You could put 0, 1, or 2. You could calculate the log of how many times it appears or whatever, but often these simple approaches work pretty well. So 1 means that the word occurs in the document and 0 otherwise, but you would still get the same idea with this matrix. Now, but we still got the issue that it's a large matrix. Now, another approach is counting, if we want to get a bit more sort of detailed information and we want to learn something about words, not just about documents, well, we could have a matrix where the rows and the columns are both words. And we could put a 1 in the matrix if words occur near each other. So this matrix here, you only put a 1 if this word occurs before this. So bought, it's not a symmetric matrix. This 6 means that the word A is followed by the word crooked. So this is like this is sometimes called a 1 gram matrix. So this is useful, again, but because it's a very small example, we're not going to get too much useful information out of this, but this just illustrates the point, and if you had many more documents, you'd get a much more, you'd get a matrix that's much more informative. Now, one thing you can do with this is use this as a word prediction model. So this is an n-gram model. Based on this information, you would say, let's say you're processing language and the previous word is A, and you want to predict the next word. How would you do that? Well, you look along the row and you say, okay, well, based on what I've seen, the word A is usually followed by crooked, but sometimes by little. But to turn this into a probability, I have to normalize along the rows. So I divide every number by the sum of the numbers in that row, and I say, okay, well, after the word A, there's a 6 out of 7 likelihood the next word will be crooked, and a 1 out of 7 it'll be little, and after the word crooked, there's equal likelihood that the word will be cat, house, man, mile, mouse, sixpence, or a style. After the word lived, the next word must be together. Right? So this gives you a probabilistic prediction model. Right, so we normalize every row to sum to 1. That gives us the probability of Wj is the conditional probability of Wj based on Wi. So what this probability says is, if the previous word was W, we've numbered all the words in the dictionary. Let's say we've got 60,000 words in the dictionary, and we've numbered all of them from 1 up to 60,000. And then they say, okay, if the previous word is W sub I, what's the probability that the next word is going to be W sub J? And this gives us a very kind of simple way of answering that question. Now, yeah, we would need to aggregate over a large corpus, right? Because if you just look at one document, unusual words like crooked will dominate the thing, right? So, but if you average over a lot of documents, that won't happen. But if you look, this does kind of capture some common phrases, like these phrases tend to occur, these combinations tend to occur not just in this document, but generally. There was, man who, and found, he bought, who caught, and they all lived together. Those are pairs of words that often occur one after the other. And if we want to get sophisticated, this is called a unigram model because it makes a prediction just based on the it makes a prediction just based on no, sorry. Oh, uh-oh. Oh, sorry, and we might not have had any audio for the first half of this lecture. That's bad. Uh-oh. Oh dear. We could generalize the unigram model to a bigram or a trigram model. By considering the n preceding words. So we could consider the 2 preceding words, or the 3 preceding words, or the 4 preceding words, or whatever. Now, here's an example. I just generated this myself. I used Shakespeare's Hamlet as an example, and just generated. So I used Hamlet and just generated a 1-gram model. What's the likelihood of the next word based on the preceding word? And you see you get text which looks, if you look at the local structure, it kind of looks sensible, but when you look at the big structure, it doesn't really make sense. So rashly, good night is very liberal. It is easily said there is, give to a sore distraction in wrath, and with my king may choose but none of shapes, and editing by this and shows a sea, and what this is mishing Malako, and gins to me a past transports his wit Hamlet, my arms against the mind impatient by the conditions that would fain know which the wicked deed to get from a deed or tutor. It does sound a little bit like Shakespeare, but it just doesn't really make sense. It's just kind of gibberish. But if you just look at a few words at a time, it kind of might make a little bit of sense. Now, sometimes we don't necessarily want to predict the next word, but we just want to know which words are likely to occur near each other. So if we have a certain word, what's the likelihood that another word will occur nearby to that word, say within a 2-word window or a 10-word window, maybe 5 words on either side of that word. So we could build a matrix in which each row represents a word and each column is a nearby word, right? So this is what happens if we construct a 2-word window for that text. And you see now we have a symmetric matrix because, you know, if we're looking at words like before and after. And if we look at a 10-word window, we get a more kind of filled-in matrix. So we're looking at 5 words, the 5 preceding words, the 5 following words, and what are the combinations that occur in those places. So if we do this, again, it's a bit like the document classification. Each column could be regarded as each column could be taken as a vector representing the word. That's the idea. So we're looking at a vector space. We want to think of this as a vector space, and we want to assign to each word a vector in such a way that similar words are assigned similar vectors. So the representation for this, so this column here could be this vector could be treated as a representation for the word mouse, and this other vector could be treated as the representation for the word they, and so on, and crooked. But the problem with this is that it's very high dimensional. Yeah? So, or you could take the rows or you could take the columns, but you're embedding the word into this 10,000 dimensional space, and that's not really very useful. What we want to do is reduce the size of the space. We want to embed it in a smaller space, but in such a way that similar words have similar vectors, right? So we want to reduce the dimensionality of this, but still preserve the relationships between words. So if we did look in this 10,000 dimensional space, it may be that similar words are occurring near each other, but we don't want a 10,000 dimensional space. We want perhaps a 200 dimensional space. So word embeddings. Okay. So if we compute this co-occurrence matrix and we aggregate over many documents, we do see pairs of words emerging which are likely to occur near each other, but not necessarily not necessarily right next to each other, but nearby to each other. So words like cat, court, and mouse, walked, mile, little, and house. They can occur in either order. You know, I live in a little house. My house is little. You know, the cat caught the mouse. The mouse was caught by the cat, right? But they often occur near each other. The other thing you'll notice with this matrix, again, the common words, there's a risk that the common words may dominate the matrix. So we would prefer to have a way of, it might be useful to kind of keep track of the overall probability of each word and then sample the more common words less so to reduce their influence. Okay, so this leads us to the issue of word embeddings. Now, as I said, what we want to do is assign a vector to each word. And, I mean, I suppose I might just sort of jump to the end here to set the context for this. So we want to, what we eventually want to be doing is we want to use like something like an LSTM to process real language, but instead of using a one-hot encoding for the words, we're going to use for each word, we're going to use the vector that's assigned to that word to input to the neural network. And the idea is that by using these vectors, we should get a better result because similar words have similar vectors. And this idea really goes back actually to the 1950s, to the structuralist linguistics movement. These are some quotes by Harris and Firth. Words that are used and occur in the same context tend to purport similar meanings. Or you shall know a word by the company it keeps. So this is the aim of the word embeddings. We want to find a vector representation of each word such that words with nearby representations are likely to occur in similar contexts. And this is an idea that has a long evolution. So like I said, the 1950s, we talked about the recurrent networks in the 1980s. In the 1990s, this appeared as like latent semantic analysis and hyperspace analog of language. And then you get this sort of language models involving recurrent networks. starting in 2000, and eventually Word2Vec and Glove. We're mainly going to be focusing on Word2Vec. So this is an example of just some word embeddings you might get from that text that we talked about. It's not very informative, but it illustrates the process. Okay, so dimensionality reduction. Now, we start with our co-recurrence matrix. Now, if we remember here, L and M are the same. So L is so the rows of this matrix are the words, and the columns might be documents or they might be nearby words. So this is a general method. L and M are not necessarily the same, but they might be the same. So we've got this matrix that's 60,000 by 60,000, and so that, as I said, the rows of this matrix give us word embeddings, but they're too high dimensional. So how can we reduce the dimension but still preserve the relationships? Well, a bit of linear algebra here. So every matrix X can be decomposed in the form, there's a thing called singular value decomposition. You can decompose the matrix into a product of three matrices U times S times V transpose, where U and V are unitary, meaning that all the columns have unit length, and S is diagonal. So diagonal means that only the entries along the diagonal are non-zero. But we can also arrange it that these numbers are actually positive, and we can juggle the matrix around. It's often convenient to juggle the matrix around so that the biggest value is first, and so that these values are in decreasing order of size. So this is L by M, so we have a matrix that's L by R, a square matrix here that's R by R, and a matrix here that's M by R, where R is the rank of the original matrix. Okay, now we can so these numbers here are called singular values, and then what we can do is we can truncate this matrix U. We can sort of throw away some of these singular values. So we might if the matrix has full rank, then we might originally have M of these singular values, but we can just throw some of them away and set them to 0 and just keep a smaller number. So because these are in decreasing order of size, we assume that the most important ones are coming first. So if we're going to keep the most important ones, it'll be if we can only keep R of them, then we keep the first R. And so once we've done this, then the kth row of this matrix U will give us a lower dimensional representation of that word. So remember, this row here was a 60,000 dimensional vector representing that word. If we choose R to be, say, 200, then this will give us a 200 dimensional representation of the kth word. And so this is the basis of all this kind of word embeddings. Now, the problem is that this singular value decomposition always exists, but it's quite expensive to compute it. Because L is the number of words in the vocabulary and M is either equal to L or it could be the number of documents, and the time required to compute the singular value decomposition is proportional to L times M squared if L is bigger than M. So if L is equal to M, it's the cube. So if it's 60,000, the computation will be 60,000 cubed, which is basically intractable. It's up in the billions, right? So we can't compute it exactly. So we have to approximate it somehow. Now, there's a method called GLOVE which tries to explicitly approximate the co-occurrence matrix based on counts of word occurrences. But the model we're going to focus on is word2vec, which is a predictive model, and it kind of implicitly performs this singular value decomposition, but not explicitly. So it's a predictive model. It's a kind of like a neural net. It is a neural network, but it's a bit unusual because it's a linear. There's no activation function. It's purely linear. But it's trained to try to maximize the probability of a word based on the surrounding words. Now, just this when a lot of people are familiar with the idea of eigenvalue decomposition, and it's natural to ask what's the difference between eigenvalue decomposition and singular value decomposition. Well, here's a couple of examples. So if we try to take the eigenvalue decomposition of these two matrices, you'll notice that the eigenvalues aren't necessarily positive. So in this case, one of the eigenvalues is negative. And in this case, both of the eigenvalues are imaginary. So the eigenvalue decomposition, you have omega times d and then omega inverse. The singular value decomposition, u and v are separated out. They don't have to be inverse to each other. And so for these examples here, well, in both cases, S is just 1 and 1. But you see u and v, how u and v vary. So here v is the identity matrix, but u swaps the two coordinates. And for this matrix, this u is the same, but v is like negates one of the coordinates, right? So by manipulating the signs here, we can keep these values positive. But what this does is it kind of decouples u and v. U gives us, so to go back to this general case, let's suppose L and M are equal and they both index the words. Effectively, we get two representations for each word. So this row here, UK, gives us a vector for the word K, and if we looked at if we looked at the kth column of this, that would give us an alternate vector for the same word, but these two representations are completely separate. So at the end of the day, we just have to choose one or the other. If we decide to choose these word embeddings, then it's all kind of logical and similar words will have similar vectors. Or if we chose these ones, the same thing, but there's no real relationship between these representations and those ones. It's completely independent. So that's one of the interesting things about this model, in the end, we only need one set of word representations, so we often end up taking this one and we just discard this. This is just used as a tool to help us to get this. Okay, so yeah, just the technicalities of this eigenvalue versus singular value. So they are the same. So if x is symmetric and positive semi-definite, then the eigenvalue and singular value decompositions will be the same. In general, the eigenvalues can be negative or complex, but the singular values are always real and non-negative. Even if x is a square matrix, it treats these two representations separately. And the word co-occurrence, so if x were symmetric and positive semi-definite, the eigenvalues and singular values would be the same, but the word co-occurrence matrix is symmetric, but it's not positive semi-definite. So for example, if the language consisted entirely of alternating, if there were only two letters in the language and they were always alternating A, B, A, B, A, B, A would be the context for B and B would be the context for A, right? So sorry, so this is symmetric. This matrix, so this is the simple, if in the case of the AB, 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 this would be the co-occurrence matrix here. And when I say that it's not positive semi-definite, what I mean is one of the eigenvalues is negative, right? And so if you're given any co-occurrence matrix such as this one, if you were to calculate the eigenvalues of this matrix, some of them would be negative. So that's just, yeah, for the math heads, the technical details. Okay. Okay, so now let's look at this word to vec model. So this is this is what it looks like, and so it's kind of, it looks a bit like a multiplication of two matrices, but it also looks a bit like a neural network. It's kind of a bit of each. So we have an input layer and we have an output layer, and each of these is meant to be a word. So this again, yes, apologise that the L has now become V, but this is all the words in the English language. You know, these are numbered from 1 to 60,000, and these are numbered from 1 to 60,000. And if you put in a word here, this is meant to be interpreted as a softmax probability distribution of what words are likely to occur near this word, right? So if the words crooked and house often occurred together, if you put house in here, then the probability of crooked should be fairly high, and if you put crooked in here, the probability of house should be fairly high. So this is a predictive model. We train this as a predictive model. We have pairs of words that occur nearby to each other. We feed in one word, and then we try to train the model to predict the other word. And this is, like I said, this is just linear. We multiply by these weights to get the hidden units, and then we multiply the hidden units by these weights to get the outputs. So we can write that as matrix. We can write this in matrix notation. So the linear sum, right? So because this representation, let's think about this a little bit more. Because this representation is a one-hot encoding, let's say the input word is house. So, and that's word number 3. So there'd be a 1 here, and everything else would be 0. So when we multiply this out, what's actually happening is whatever weights, all that matters is the weights from this unit to the hidden units. Whatever the weight is from this unit to that unit will get copied to this unit, because that'll get multiplied by 1 and everything else will get multiplied by 0. So what actually happens is that these the weights from this unit get copied into here. There's no bias. And so what ends up in these hidden units is just these weights, and this can be regarded as the embedding for that word, right? And then these things get multiplied out, so then if you want to find out what the output, let's say word number 1 is crooked, you want to find out, well, what's the activation for the word crooked? Well, you take each of these weights, you take each of these hidden unit activations and multiply it by the weight from there to this unit. So actually another way to think about this is you look at these weights here into this unit, and you take a dot product of those weights with this set of hidden units. So some of you may need to brush up a bit on your linear algebra, but that's actually what's written here. That the weights from here, the weights from this unit to the hidden units can be treated as a kind of the representation of this word, and these weights to this unit can be treated as the alternate representation for that word. And then when you take the dot product, this gives you the softmax activation, and the dot product is written like this: Vj transpose V Vk. So you're looking at the kth word here, the kth word here, and the jth word there, and this activation would be U. The output activation Uj is Vj transpose V prime J transpose Vk. So it's a dot product between this set of weights and that set of weights. So that's the outputs, and then we apply softmax to those outputs. So the probability of word J occurring in the context of word K is this softmax function. So we assume the probability is proportional to the exponential of Uj. We have to divide by a normalizing constant. And if we substitute in the formula for Uj, it looks like this. And what we're seeking to maximize is this formula here. So we remember the text consists of this long sequence of words. And so what this formula is saying is the C determines the context. So if C is equal to 5, then we're looking at the 5 words before the word and the 5 words after the word. And this is saying for any word, so the notation has, there is a bit of an abusive notation here. So W, here Wj, the Wt here refers to the teeth word in the document. So if T is equal to 100, this is the 100th. If you read through 100 words in the document, this is the 100th word, and then this is words 95, 96, 97, 98, 99, 101, 102, 103, 104, and 105. So for each of those words, you want to maximize the probability of those words being predicted based on this word, because those are the words that actually occur in the context of the middle word. Okay. Are there any questions about this? Okay, so it's a linear model. There's no activation of the hidden nodes. Now, so there's two kind of ways to do this. One's called continuous bag of words. The other is called skipgram. That essentially give pretty much the same result. I'll explain the difference in a minute. The other issue is that we need to be computationally efficient because the softmax, in order to compute the softmax, we need this normalizing constant, and the normalizing constant we have to add up the outputs for every possible word in the dictionary. So we have to add up 60,000 numbers to get this normalizing constant. Okay, so we need to have a faster way of doing this, and we're going to talk about two fast ways of doing this, which are called hierarchical softmax and negative sampling. And there's this issue about sampling frequent words less often. So there's a few little kind of tricks here that people have played around with to just try to get the best performance out of the system. I will also mention this thing about softmax. It was kind of in the early 2000s that these methods were developed. Very recently, because GPUs have become so much bigger and faster, some people have actually gone back to just using the full softmax and just calculating this for every word, because they've got so many, the computers are they've got access to computers that are so big. But those of us who are mere mortals and don't have massive supercomputers still need to use these kind of tricks. Okay, these are the details about the word updates. Now again, these look a bit unusual, but if you just work through it all, it's all kind of straightforward. So remember that we're doing a softmax over these UJs. So if you take the log of that softmax thing, you get the log of the denominator, and so the log of an exponential is the log of x of uj is just uj, and then you have to subtract off the log of this. So you get the output for the correct prediction, and then this is the term that comes from all the incorrect predictions. And we want to treat it as something we're minimizing rather than maximizing, so we take the negative. So that's the loss function. Now, when we differentiate, we're just always differentiating linear functions. So the derivative of this loss with respect to uj, if j star is the correct prediction, then the loss is minus, if it's the correct prediction, we get a -1 here. And then we always get this derivative of this log term. So I think if you've worked through the exercises, there's an exercise that helps you to understand about softmax. So it always increases the probability. It always tries to increase the output for the correct class, and then it tries to decrease the output for all the other classes, but if it gives particular emphasis to the wrong ones which have been given a high probability. In fact, the correction here is proportional to the probability that's been assigned to that incorrect word. And then, again, this is just differentials of linear functions. Yeah, so this can all be trained quite straightforwardly. All right, now the difference between continuous bag of words and skipgram. So there's sort of two ways to do this. Remember, we're given 10 words. Because of the context, we're given 10 words surrounding a particular word, and all 10 of those words are treated as predicting that one word. And so we can save time, because the middle word is always the same, but the 10 surrounding words are different. We can save time by training it all at once instead of 10 separate times. And there's two ways to do it. So we could present the 10 surrounding words and try to predict the middle word. That's called continuous bag of words. Or we could present the middle word and try to predict the 10 surrounding words. We could do it either way, and it usually more or less ends up with the same result. Now, note the difference here between, this is interesting, the difference between this and net talk. So if you think about net talk was similar, but if you remember net talk took the 3 preceding letters and the 3 following letters, but it treated each position differently. So it had one set of weights for the word that was the character that was 3 back, and a different set of weights for the one that was 2 back, and a different set of weights for 1 back, and then so it had different weights for all these different positions. You know, the letter that came immediately before was treated differently from the one that came 2 before and the one that came after. But with word 2 vec, we throw away the information about where the word actually is. We treat all of these surrounding words the same, and because it's a linear model, we can do this by actually adding these things all up. So effectively what we're doing is we take the vector representation of each of those words and add them all together. So we're adding together the 10 words, and then from that, so this mixed hidden unit in the middle is like an average over those 10 words, and from that we're trying to predict the middle word. Now, or alternatively, we could feed in the middle word and then try to predict all of the 10 surrounding words individually, right? So these two methods, yeah, pretty much give the same result, but one of them, for implementation reasons, one of them may be faster than the other. Okay, so how can we speed this up? Okay, so I'll talk about the speed ups and then the subsampling. Now, all right, so let's concentrate on this continuous bag of words model. So we're training this thing. We've got 10 surrounding words. We feed them all in here and we get a linear layer. And then with this output layer, in order to train it, we've got one correct word and 59,999 incorrect words. So if we calculate this full softmax, we'd have to calculate the output for every single word and add them all up and then do the softmax. Now this, at least until recently, was considered computationally too expensive. So how can we speed that up? Now the first method that was developed for this was by Bengio in the early 2000s. He said, well, what I'm going to do is I'm going to arrange the words in a Huffman encoded binary tree. So this is kind of why we went through these exercises of these Huffman trees, so that we'd understand this. So you just look at those 60,000 words and you calculate the frequency of each of those words, and then you build a Huffman tree. And then each output of the network is going to correspond to a branch point in the tree. So let's say this is the Huffman tree here, and this is the word that actually occurs in that context. This is actually the middle word. Well, I sort of trace down the tree to see which branches I have to follow to get to that word. And instead of the network trying to directly predict the probability of this word, the network tries to do this in stages. It first tries to predict, well, what's the probability that the word is in this half compared to that half? And then once you get to here, it tries to say, well, what's the probability that it's among these words or these words? So at each branch point, you have a probability that divides the nodes into two groups, and you have to calculate the probability of the word occurring in one group or the other. So you have one output corresponding to each internal node of this tree, and you only calculate the outputs that you actually need. So if this is the correct word, I don't need to calculate this node or this node because my path isn't going to go through there. I only need to calculate those nodes that I actually pass through. So I use this node. The output of this node is treated as I use a sigmoid at this output for this node, and the sigmoid tells me the probability of, gives me a number between 0 and 1, which is interpreted as the probability of branching right, and 1 minus that will be the probability of branching left. So if this is correct, I train the network to make this choice rather than that one, and then when I get to here, I train this node to make this choice rather than that one, and here I train it to make this choice instead of that one. So the number of nodes is still the same. The number of output nodes is still the same, but not all of them are going to be calculated, right? So if there's 60,000 leaves in this tree, that means there'll be 60,000. If there's this is the thing about a binary tree. If there's 60,000 internal nodes, there'll be 59,999 internal nodes. So the number of outputs is the same, but I only need to calculate the nodes that actually occur along this path, not the others. And this is a small example, but in general, the number of nodes visited is very small. It's just the log of the total number of nodes. If there's, log base 2, log 60,000, log base 2 of 60,000 is 16. So I expect to have to calculate only 16 nodes on average. And this is just a fancy way they came up of notating what I just described. So this equation is a little bit complicated, but this is saying you have a probability of branching here, and a probability of branching here, and a probability of branching here, and so the probability of choosing this word is actually the product of all those probabilities, because I choose this word if and only if I've made all of those choices correctly. So the probability of choosing this word is the product for all the nodes along this path of the sigmoid of the output of that node. And then multiplied by that corresponding output, and times the hidden node. Right. So this equation does kind of make sense, but they've just made up a very specialized notation. Any questions about this? All right, so this is nice because it's very formally correct. This thing is precise, is formally equal to a probability. but there's another way of achieving the same thing which is a little bit hacky but kind of gives reasonable results. And this is called negative sampling. So the way negative sampling works is the following. You know, I've got a particular word which actually occurred. So I've got a particular word which is correct. Instead of calculating the probabilities for instead of calculating the outputs for every single other word and turning it into a probability, what I'm going to do is just randomly choose a certain number of other words, and I'm going to train the output of the correct class to be bigger, and I'm going to train the output of the incorrect words to be smaller. So instead of the 60,000, maybe I just pick 20 words at random that didn't occur. I'll train the network to reduce their activation and then correspondingly increase the activation of the word that actually did occur. So this is called negative sampling. So we just choose this subset of words, W neg, and then we try to increase the log of the, again we have this sigmoid activation function. We try to increase the log of the output of the correct word and decrease the log of sigma. I think I got a sign. I better check that. There might be a sign wrong there. One of those is supposed to be negative, I think. So we try to increase this and decrease this. Log of, I think the negative sign is actually in here, right? So the sigmoid, by reversing the activate, notice that there's a negative here and not here, so by reversing the activation, sigma of negative x is 1 minus sigma of x. So by putting this negative in here, this gives us the probability of the word. This is the probability of the network predicting that the word doesn't occur, that the word is not correct. Yeah. So the equation is correct, but the negative sign is in here, not here. Okay. Now, as I said, the sort of mathematicians who like to prove theorems about this prefer this because it's like more theoretically pure. It gives you a probability. This thing here doesn't actually give you a probability. It just gives you a kind of mix of different probabilities. So you can't sort of theoretically prove that this is going to converge to what you want. But in practice, it usually does give a very good result. Now, how many negative samples do you need? Well, for small data sets, you need about 5 to 20. For large data sets, you can often get away with just between 2 and 5. Again, these are things that are just determined empirically. There's no theory behind this. Now, from what distribution should you draw the negative samples? Now, again, this is just empirical. So you think about it, some words occur more than others. So one possibility is I could choose words based on the probability with which they occur in the text. So I'm choosing common words more often and rare words less. That's one extreme. At the other extreme, I could say, well, I'm going to choose all words with equal probability. There's 60,000 words. I'm going to choose all of them with a probability of 1 over 60,000. But it turns out that you get better empirical, or you could take the square root. You could say, all right, well, I'll calculate the probability of a word occurring, and I'll take the square root of that number. So that would be a kind of compromise. You're choosing common words more often, but not as often as they really occur. And it turned out, after trying several things, instead of taking the square root, they take, so the square root would be the probability to 1/2, so they actually take it to the power 3/4. So it's sort of roughly approximating the distribution of the words, but changed a little bit so that the rare words are boosted up a bit and the common words are pushed down a bit. And rather than just taking the overall probability, they use a unigram distribution based on the previous word. So they train a unigram model. They say, okay, based on the previous word, what words are likely to occur after that word? And then they choose it with this probability. So it's just, a lot of it's just these little hacks and little details that people figure out by trying out different things. We also sometimes throw out words that occur more frequently. So in this continuous bag of words model, some of the words surrounding that word might be the, or a, or and. So these very commonly occurring words sometimes can distort the statistics, and you want to kind of sample them less often. There was, in the very early days of the World Wide Web, before Google, there was a couple of other people who tried to do search engines, but they didn't do such a good job. One of them was Alta Vista, which was made by Digital Equipment Corporation, and it tried to predict if you typed in a search term, it would try to give you web pages where those words occurred very often. And there was this famous page, it was called the page, and this page was a web page that had text on it, and every second word was the, and the other words were like the most, they took the most common 200 words in the English language and put them in, and then every second word was the. And so if you typed in a search query that had the word the in, it was very likely to bring up this page, because the page had the word the occurred 100 times, and you typed in the word the, so this page must be very relevant. So there was people who were trying to fiddle around and fool some of these naive systems. So in order to avoid that kind of bias, we throw some of these away. So we take the 10 words before, the 5 words before and the 5 words after, but if the word occurs commonly, we may decide to just throw away that word. And again, they just empirically decided that this was the best way to throw away the words. You look at the frequency with which that word occurs, and then you divide some constant by that frequency and take the square root. And don't ask me why that gives a good result, but apparently it does. So common words are likely to be excluded. Okay, so that's word to VEC. Any questions about this? Yeah. How are we doing? Okay, I'll just make a couple more remarks, and then some of these other models we'll discuss next week. So what can we actually do with these word embeddings? Well, so we'll talk later about how we can use them in combination with LSTMs and so on. But another thing we can do, and this in a way is just a bit of a test to see whether the word embeddings are good or not, is we can use them to try to answer questions that you sometimes see on IQ tests. So seeing the pictures of our old home made me feel something and nostalgic. Which word is most likely to go in that context? Because so we can use this these word embeddings. You think about this, how would we use the word embeddings to answer this question? Yeah, sorry, I might just mention, so these kind of words commonly occur in things like the Scholastic Aptitude Test and on IQ tests. They test your knowledge of the language. Sometimes you have to know some pretty obscure words in order to answer the question. But there's been a long debate about this because not only do you have to have a very good grasp of the language, but sometimes you need specialized knowledge about a particular country so they can be culturally biased. You know, because the House had the votes to override a presidential veto, the president has no choice but to, you have to know something about the American system of government to really answer this question. If you come from another country with a different political system that doesn't have a president, you might not be able to give a sensible answer, right? So people have complained that these tests may be biased towards certain people from certain cultures. So how do you answer this question? Well, what you do is you treat these words as the context, you feed them in, that gives you a hidden vector, and then you basically, of these four words, you calculate the probability that the model predicts for each of those four words, and whichever one gives the highest probability, that's the one you choose. Yeah, so this gives you a quantitative, at least it's not perfect, but some quantitative indication of whether it's a good model or not. Now, these word vectors can also help us to understand linguistic regularities. So, for example, if you take these, I don't have a picture of this, you have to kind of imagine it, but these are vectors, and you can add vectors in a vector space and subtract them. And it turns out that if you take the vector for king and add the vector for woman and subtract the vector for man, you get something very close to the vector for queen, which kind of makes sense. And this is sort of what I mentioned at the beginning of teasing apart the different attributes. King and queen are similar words, but they differ in one respect, and they differ in the same way as man and woman. Another way of writing this would be king minus queen equals man minus woman. Yeah. So this gives us a way of answering another type of IQ test question, which is of the form A is to B as C is to what, right? So king, this could be phrased as king is to man, this could be phrased as man is to king as woman is to what, or it could be phrased as man is to woman as king is to what, right? There's different ways of phrasing the same question. So if you want to answer this question, you take the vector for C and add the vector for B and subtract the vector for A. And then you want a vector that's very close to that vector. So for every possible word in the dictionary, you calculate the dot product of these two things and then divide by the size of this. So you're kind of calculating or you can calculate the angle. Sometimes you just calculate the angle between the two vectors. This is sort of like calculating the angle between the vectors, but the size of x also plays a role. It's the component. This is the component of vector x in the direction of this vector. So we can answer these sort of questions. Evening is to morning as dinner is to what. Bow is to arrow as what is to bullet. Right? And we can adapt this to a number of different contexts. So capital cities, well, these diagrams are, so in order to get these diagrams, people have trained Word2Vec. They've got a 200-dimensional representation or a 100-dimensional representation for every word, but then they select out particular words and do a kind of what's called a principal component analysis. They try to extract, just for visualization purposes, they try to extract out the 2 dimensions that carry the most variance for these particular words. And you can kind of see the vector joining a country to its capital city is quite similar, right? So China, China is to Beijing as Turkey is to what? Very likely you'll come up with Ankara, right? So you can see these relationships. And here's other examples. Capital cities of countries, the currency of a particular country, a large city and a state, these gender relationships, king, queen, brother, sister, and so on. And then also grammatical relationships, so opposites, comparatives, a country and its nationality, present, past tense, and so on. So you can try out all of these different things, and then you get things like, you can train on certain relationships and try to use it to predict others, and generally it does a pretty good job, although occasionally it makes a mistake. Can anyone see a kind of a mistake in this table, or something that's not quite what was what we were looking for? It's a bit. Last year, a Russian student noticed this straight away. The network thinks that the president of Russia is a single person whose name is Putin Medvedev. Right? These guys, they swapped. They worked as a team and like swapped roles. One was the prime minister and the other was president, and then they swapped. When the term limit expired, they swapped back and forth. So they're so closely associated that the network thinks it's one person. I think there was another mistake here, but I can't remember what it is. Yeah. So you get a few odd ones, but mostly it's pretty good. Okay, I think we have to end there. Next week, I'll talk a little bit about how to sort of use these word vectors to build these neural translation and bigger systems like that. And then if we have time, we may move on to the next topic. Yeah. Good. And I'll try to do something about the audio. So this is just saying that get two different representations. So these words and these words may be the same, but this vector is totally different to this vector. And the same thing here, like the weight, this word and that word may be the same, but the weights from here to here, the weights from that node to here and the weights from that node to here are totally different.
So what's the source of the channel?
Well, here, in this simple case, let's have a look here. Well, here, if it was an eigenvalue decomposition, then the rows of omega would be the same as the columns of omega inverse. So you'd have the same representation at both ends. But because it's singular value, the rows of this and the columns of this are different.
So you are the way source are target.
That's right.
The same thing, I was not really sure about the same thing which I was asking previously, vector.
Yeah.
I can't understand the grouping exactly. So you said one group is the window of size 7, but why is it grouped based on the alphabets? So the window could be like one alphabet could be A, the other could be E, the other could be...
Yes.
So how would you group it based on alphabet? You said 7, like 26 alphabets plus extra 3 characters.
That's right.
Each of them having 7 letters, as in each with